Well, first of all, I have to thank the organizer for this invitation. And, well, the title is self-explanatory. I will be speaking about spectral theory and some class of models in spectral theory of random operators in the general framework of what is called Anderson localization, problematic Anderson localization theory. Okay, now let me see. Yeah, so what is it about in general anyway? Like I said, it is a spectral analysis of random operators, and in general, and that was at the origin of physical and mathematical Anderson localization theory. People considered, first physicists, let me stress it again, the energy operator of a quantum mechanical system with a configuration space ZD, just the lattice. It may be physical, D equal 1, 2, 3 or more. D is maybe arbitrary. Okay, now this Hamiltonian is a sum of two terms. This is a single particle approximation. There's only one particle, quantum particle, moving in a disordered, let's say, random environment. So we have the free kinetic operator. Say on the lattice, you take the canonical graph Laplacian, just second order, most classical Laplacian on the lattice, with a parameter epsilon measuring the mobility of the quantum particles. Alternatively, we can put the inverse of epsilon, just scaling everything in front of V, and then it will be called the disorder or randomness parameter. Okay, this guy is deterministic, it is constant, but this operator of multiplication by V of X and omega, where X is a site on the lattice, it's a physical point in the space. And this is a random parameter relative to some probability space omega with measure P, whatever this measure might be. Then we have actually as a potential energy, a sample of some random field in general sense of the word. However, I will not be speaking about the case which was in the origin, was just a ID random field. On the lattice, it's a bona fide random field, not generalized. But rather, we take V of X omega as the values of some sampling function or Hall function. At the point of phase space omega, now omega is becoming the phase space of some dynamical system with time ZD. Okay, so every time we change the starting point, we get another sample. One particular example or class of examples is when omega is a torus of whatever finite dimension, and the dynamical system is generated by the mutually incommensurable shifts alpha I. Let's say nu is equal to 1. There is just one alpha, no indices, and Tx omega is omega plus X times alpha. So there is, of course, a big difference in the randomness, in stochasticity of an IID field and this one. And this corresponds in physical applications to different situations from the physical point of view. Now, what is the general formulation of the Anderson localization problematic? One has to determine if the proof, if possible, or disprove that with probability 1, the Hamiltonian H, which is random, has a point spectrum only point spectrum or point spectrum in some interval according to the case. Well, very briefly, and not for discussion because I have very limited time, there are some classes which were extensively studied before, starting with the early 1980s. First, the Maryland model, introduced, first explored by a team of physicists, Grempel, Fishman, and Prange, and then mathematicians, Pastor and Figotin in the Soviet Union, and Avron and Simon in the United States, proved what physicists established first, that in this model, with such a quasi-periodic potential V, one has a complete localization. That is, all the spectrum is pure point, and all the eigenfunctions decay exponentially at infinity. This was not a perturbative result. There is no need to put some small parameter in front of delta or large parameter in front of V. It is not perturbative because there are deep algebraic, let's say it, algebraic or analytic results. It doesn't work for anything except tangent. Well, in '83, just a year later, another team in Marseille, CNRS Marseille, Belissard, Lima, and Scopola, proved that perturbatively, for small epsilon, the complete Anderson localization holds also for Maryland-like models, where V is meromorphic in some strip around the real line with one pole per period. And it is on this period, it is monotone increasing or decreasing, but strictly monotone. Okay, this is of course a very particular situation, and more and a model closer to real world applications was the cosine model, or almost mature model or Harper model. There are many authors, and I would certainly insult some of them if I start quote some and forget about the others. Okay, a cosine-like model where V is not exactly cosine, but it is a Morse C2 function with one maximum, one minimum on the torus, was done with a slight shift of time by Sinai and by the team of Fröhlich, Spencer, and Pitberg. 1987-89. The next fundamental step was done by Bourgain, Goldstein, and Schlag in different combinations by 2 and by 3. They prove that for a large number of classes of analytic functions on the torus, first it was just nu equal to 1. One still does have localization, complete localization, but it was again a perturbative result. Now, what about non-analytic V? That's here we come closer to the topic of this talk. It proved to be very difficult to treat such models with V, let's say, of finite smoothness, CK, or just continuous on the torus, and treat every V of some class of functions described in its regularity properties, in terms of its regularity properties. So, taking account of this difficulty, some 10 years ago, I proposed some compromise. We still have functions on the lattice generated by the Hall-school sampling functions on the torus. It may be other things than a torus, but torus provides very constructive, very clear examples of applications. But we don't take just one Hall function. We take an entire family of them, parametrized by a point in some parameter space, and it proved to be very useful to assume that this auxiliary parameter space is itself a probability space. This probability has nothing to do with, so to speak, randomness encoded in omega. This has nothing to do, which means whatever be the choice of the half function v indexed by theta, we will still have a quasi-periodic potential if we have this dynamics given by perpetuals. It's not only the shifts of the torus which can be considered, but let's say we stick to them. Now, what is proved? Well, to move further, I have to briefly introduce this classification proposed by it was Del Rio, Zhytomyrsky, Last, and Simon long ago. Euler and Sule, uniform or semi-uniform localization of eigenfunctions. The semi-uniform localization of eigenfunctions that one most frequently is able to prove comes back to the beginning, the very beginning of the mathematical understanding localization theory, which started in 76-77. It was in 76, when I was a second-year student, that one of the keynote speakers to this conference, Stanislav Alexeyevich Molchanov, gave the first talk at a meeting of the Moscow Mathematical Society about a continuous, not lattice, but continuous model in one direction, in one dimension. Okay, so localization does have an exponential decay at infinity, does take place for every eigenfunction of this random operator. But the localization center, see, here in the exponent, we measure the difference not from zero, but from some center xk. Well, it should be xk with a hat. And of course, there is some random constant in front of it, which means that eventually, in fine, this eigenfunction starts to decay grosso modo with exponential rate m, but only eventually. For some time, for quite some time, or the space in ZD, it may be like cosine or sine. It can be oscillatory and not decay. Okay, so this is semi-uniform. There is something which varies randomly from one function psi k to another. Euler is the case where C and xk are absolute constants. Xk is relative to psi k, and speaking informally, each psi k is localized, is concentrated mostly around, say, the side on the lattice k, but ck is non-random. This is uniform decay. So how could one prove uniform localization of eigenfunctions for quasi-periodic operators? Not really, essentially for the same reasons for which Euler fails in many models, as was written on the previous slide. It is a very rare situation, very rare situations where Euler does take place. So the model I proposed was the following. So we have a function, a half function. It is not a function of x. It's a function on the torus, and omega is on the torus, which is expanded in a series which can be exactly a Haar-Weber series, or mimicking the most important, most fundamental properties thereof. In which sense? we have an infinite number of generations of functions phi nth and with subscript k of omega on the torus. Each one is modulated by, first, a coefficient which depends only upon the generation. It is constant, it is non-random. And one needs here super exponential decay, like, say, exponent of minus n squared, at least n to the power strictly greater than 1. And there are individual modulators, which are, so to speak, random. They, theta and k, vary in the auxiliary parameter space, large capital case theta. Again, phi can be exactly Haar wavelets, but not necessarily. One does not need this series to be orthogonal. For example, if we take, so to speak, half of each wavelet phi, that is the indicator function of a subinterval of length 2 to the power n in the nth generation, it will be just fine for all the technique to work. It does work for the orthogonal Haar series and non-orthogonal pseudo Haar. However, what is important is, first, the super exponential decay of the generation coefficients and the exact constants of each function phi and k appearing in this expansion. Well, there are other situations where such a hull is good for the techniques I'm going to present on the level of results, but let us stick to this one. Okay, so what is proved? Well, first of all, uniform localization of eigenfunctions does take place for a class of such parameterized hulls. And not only that, one can also establish the so-called Minami, or rather Minami-like second order eigenvalue correlation inequalities, relations in form of inequalities, of which I will speak in at the very end of the talk. Now, why the harsh, well, this some artistic creation, Haar from the Haar's wavelets, and harsh because each function is a step function. It is not a regular at all. It is not even a constant. Of course, it doesn't mean this series has a sum which is piecewise constant. It is not. But the set of its values is fractional of zero Lebesgue measure by choice of an. So unit does take place. And why this harshness of the functions phi and k and decay of an gives rise to uniform localization? I cannot, in the time allotted to explain it in a full generality, but let us say, why can one with the harsh potentials assure that by a proper choice of theta, by proper choice of this random amplitude phi and k in front of Haar wavelets, we can guarantee that for whatever omega, we have never proximity, non-tolerated proximity of v at site x and v at the next, at the nearest neighbor x plus 1 with the same omega and theta. Okay, it is better to be explained with a picture. So here it is. The torus is now a circle. The dimension is 1. The dynamical system is generated by shifts. So from one point to another, we go by the shift vector alpha. Okay, this corresponds to shift by alpha. Now, if we take the generations up to the fourth one, then the supports of the functions of the siblings, Haar siblings, phi and k, phi 4k, k from 0 to 15, partition the phase space, the circle, into pieces which are smaller than half of the distance between tx omega and the next one, tx plus 1. And this does not depend upon the exact position of omega on the circle. This is one example. This is another one. But whatever be the starting and end point pair, this one and this one and that one, between the two red points, starting and the final point, we have intervals which separate the supports of phi and k here and phi and k here. This does not depend upon omega. And this uniformity in omega gives rise to the uniformity of localization. That is, changing the, so to speak, true randomness in the primary probability space, omega, on the torus. This distance is measured on the torus. We have the same behavior for any trajectory. Okay, so this is, of course, not proof of anything, just idea of how simple geometry and some very specific hypotheses about the structure of the potential give rise to a class of quasi-periodic models where localization can be proved to be not just semi-uniform, but genuinely uniform. Okay, and the last topic, I still have a few minutes. What is it about Minami estimate or Minami-like estimates for the EV concentration? Look, we have a random operator. It has a random spectrum. The spectrum of a given operator H lambda, omega being fixed, is a subset of a real axis, of the spectral axis. So it is a point random field, generalized random field on the lattice. Oh, no, sorry, on the real line. So considering this field as random field, what can we say about the two-point correlation measure? Is it regular, for example? If the model, if were not quasi-periodic, as it is in my talk, but the original Anderson model, going back to 1958 in physics and 1977 in mathematics, then one can prove that if we take, one can, not me, it was first proven by Minami and then developed by many authors, further developed by many authors. If we take an interval on the spectral lattice of length, which I denote by as like modulus of I, small or large, it doesn't matter, then the probability, then at least two eigenvalues, random eigenvalues of this H lambda of omega fall into the same interval. It is quadratic both in the size of the interval and in the volume of the finite subset of the lattice to which we restrict operator H, thus obtaining H lambda. That was the original Minami estimate, and very rapidly after that, shortly after that, several teams of mathematicians proved the extended Minami estimate to any finite number of eigenvalues. That is, they treated the correlation functions of all orders, all finite orders. However, look, here we have both eigenvalues falling into the same interval. How about one eigenvalue falling into I1, I sub 1, and the other one to I2. Surprise, surprise, this problem is much harder. There have been some developments, but not many, and all in the framework of spectral analysis of fully developed randomness, with V of X omega, which is the IID regular random field on the lattice. Here we don't have IID, nothing close enough to IID. Well, still, this can be proved, and that was proved about a year ago. Only an archive preprint is available because the principal text is pending submission. It is not exactly the Minami estimate, only Minami-type, because the volume dependence is no longer optimal. I mean, optimal if we take the IID case as a reference point. Then we have the upper bound for this probability, lambda 1, small lambda 1 eigenvalue falls into I1, another one to I2. And both traces are non-zero, that is greater or equal to 1. However, it is optimal in the sizes of the intervals I1 and I2. The proof is actually based not just on the proof of localization, which is to be proved anyway, but also in some smooth analysis of all spectral quantities like eigenvalues and eigenfunctions. Smooth dependence of all these spectral objects upon the point-like perturbations at every side of the lattice. So it's a quite technical thing. There is a preprint is available, and the talk as such is basically over. And the last word, really the last one, that the analytic engine powering all these proofs is not what is called multi-scale analysis or of fractional moment analysis. It is the KM-like method, which is used in a version very close technically and in the spirit to the method used by Yakov Grigoryev Sinai in 1987 to treat the cosine-like problem. Okay, now the talk is over, and I'm open to questions. Thank you.
Sure. And what is the result, anyhow? What is the result you formulate? Then what is the result?
Okay. First, with the help of Kolmogorov-Arnold-Mosel type approach, I proved a slightly different version of the result proved earlier in 2017. It was not on the list, but it is in 2017. That localization is uniform for this harsh model. And also, I proved that the dependence, the parametric dependence of all spectral objects, like eigenvalues, which are random, well, quasi-periodic not, but they are random, and eigenfunctions, is smooth for just one eigenfunction, one eigenvalue, or a finite number of them. And using this smoothness, auxiliary result on smoothness, I was used to prove this analog, or weak but still analog, of Minami-type estimate, which is non-local. Non-local in the sense that these intervals for one eigenvalue and for another one are not located nearby. I1 and I2 can be located arbitrarily on R. Classical Minami estimate is this, only one interval.
May I ask, in this
And for independent for IID potential, Minami-type estimate for two intervals we obtained before, or you obtain also it?
No, I didn't obtain it. I did not treat the IID model.
But it is known as the Minami-type estimate for two intervals. It
For
was true.
To the best of my knowledge, I maybe may not know about the most recent results. This is not impossible, but to the best of my knowledge, one can prove such analog of a two interval estimate. Only both I1 and I2 are close to each other, and the distance between them is of the same order as their magnitude, as their length. To the best of my knowledge, for arbitrarily I1, I2, the IID case seems to be hard, to remain hard one.
Yeah, but anyhow, in the previous slide, there was formulated some two interval estimate. It doesn't prove at all, or it is proved in some situations. The last time.
No. I say it was much harder, and again, to the best of my knowledge, it is not proven in great generality. For I1, let's say of order of, let's say, delta, and I2 again of length of order of delta. This distance between them, I1 and I2, again of order of delta. There is an analog. It was, well, I can give you later the reference, but it is known only in some special situations. For arbitrarily located I1 and I2, unless I'm out of the field and I missed something, to my knowledge, this is not proven. The IID model.
Thank you.
However, just to complete the answer to your question, if one is able, if one will be able to prove the analog of this complete smoothness parametric results, which I briefly mentioned, then it will be the way to the proof of general estimate.
What is smoothness? What is smoothness?
Okay. Okay, let me get back. Now, let's see. In this model, we have in front of each function, which, well, any random field can be expanded in some series if it is not very wild one, the random field. If we perturb theta and k in such a way that only near some point x and nowhere else the potential is regal, and all the other values of the potential are kept fixed, then we have one parameter of potentials. One parameter of potentials, one parameter of family of operators, and one parameter family of eigenvalues and eigenfunctions. In this one parametric picture, does this dependence upon the single parameter that we regal smooth or not? Take two eigenvalues and consider a vector of two eigenvalues. Is its evolution will be regal one parameter at x1 and another one at x2 smooth? In which sense? Which upper bounds? This is the case which I studied. In the harsh, this AA case, the occurrence of Euler reflects the fact that there are no complications which are inevitable in the ID case.
Okay. Thank you.
Thank you.